Okay, welcome back. Happy Wednesday. Happy day before Thanksgiving. Thank you all for being here. It's pretty quiet out there in the halls at GCC, so I appreciate your attendance today on this day before Thanksgiving. Thinking about our calendar, the quiz, the take-home quiz is due right now, so throw it directly in those folders. If you have it partially done, you're going to throw whatever you have done inside the folder. I don't take them after right now, so put those quizzes in the folder right now. Today we are going to do our second of 2 days on exponential functions. And then it said here there's no homework number 31. So, and I mentioned this the other day. Okay, so it's sort of true, but sort of not true. I learned this morning. There's no My Math Lab homework 31. That part was true. But there actually is a homework 31, and you're going to find it in your packet. So everybody flip right now to page 68. Page 68. Right up there at the top, you see it says homework for class 31. Right, that is the homework assignment. So I think this is the only homework assignment that isn't on My Math Lab. It's right there on page 68. I am not going to collect this. I'm not going to grade this. I'm not going to give you credit or not give you credit for this, but you should still do it because you're going to be tested on this material, okay? So you're doing it for practice. It's just not going to count for a grade. The little handout, go ahead and grab one that's on your table, little half sheet. That half sheet is the answer key to the problems on page 68, okay? Now, fair warning, this half sheet was created by one person and looked at by only one person, so there might be mistakes. It has not been double checked by anything. So if you feel like you know what you're doing and you disagree with an answer, don't spend 2 hours trying to get the answer on this key. Might not be right, all right? Also, questions 5 and 7 on page 68, you can put a line through. 5 and 7 on page 68. You don't need to do either one. Okay. All right, I think that's good there. Okay, right, and then so the rest of the week, GCC is closed tomorrow and Friday, and also there's no night classes tonight. Any questions on the calendar? Okay, then let's go through some of the highlights here on page 63. I've already filled in this equation for the increasing by 1,000 rabbits per year. So it starts at 1,000 rabbits, that's right there, and then it gains 1,000 rabbits per year. 1,000t says 1,000 rabbits per year, okay? What kind of, it's a one-word answer here. What kind of function is p? Not exponential, linear, right? That is a linear function. And in part B, let's just jump to the equation. What equation did we come up with here? 1,000 times 2 to the t. That's good. What kind of a function is that? Exponential. And oftentimes, if we describe something as being exponential, we follow it by a word, either decay or growth. In this case, growth, right? The rabbit population is growing, so that's an exponential growth equation. Last night, I started watching Zootopia. Have you guys seen that animated movie? Yeah, so go watch it again, but now you'll have a, like, with the understanding about exponential growth and stuff like that, you'll appreciate it on such a different level. Yeah. It's about rabbits. Anyway, one rabbit in particular. All right. Okay, so then here, instead of giving you data, we're giving you straight formulas, and we want to know what kinds of functions are they and what are the initial populations and things. So initial population for A is 300. 300 plus means you're starting with 300. What's the initial population for B? 270. Actually, if I'm being precise, it's not just 300, it's 300,000, right? Because all these guys were measured in thousands. Okay, so 270,000 is good. And C? 600,000. Okay, so we've got these 3 different formulas that describe the populations in these little cities. And we want to describe what's happening in each of them. Okay, city A's population. What is this 1.3T? What does that do, Ivy? It's 1.3 thousand. Said another way, how many? Right, that's the same as 1,300. People per year. And I like getting that word linear there like Ivy did. Right, so we're gaining 1,300 people per year. That's the 1.3T. How about city B? What are we gaining there? 2.1%, right? Remember this idea of there's always a 1 plus sitting inside of that number. And so if we get rid of that 1, then what's left over is the 0.021, which is 2.1%. So gain is 2.1% per year. What kind of a function is that? That's an exponential. Growth or decay? That's an exponential growth, gaining 2.1% per year. All right. The last one is potentially the trickiest one. I just got through saying that every exponential formula has a 1 plus buried inside. But look, that number is smaller than 1. What does that mean? It's a decay, right? It's 1 plus something negative. It's always 1 plus, but in this case, the number we're adding to 1 is a negative number. So what is the number that's sort of missing from that guy? Is, 0.022, yeah? So you just take 0.978, subtract 1, just like we took 1.021 and subtracted 1. It's consistent. It's not like it's a different case. Just subtract 1 every time. And in this case, negative 0.022. And so that's negative 2.2%, right? So as a sentence, what are we going to say? Loses or decreases. So loses 2.2% per year. Notice that we didn't put the negative in there. What word took care of it? Loses, right? So it would sort of be redundant to say loses negative 2.2%. We don't want to say that. Okay, exponential what? Decay. Okay, because we are decreasing. Good? Okay, next page. So first of all, a couple of numbers in this table are wrong, specifically the bottom right 3. Can you cross off those 3 and put the numbers I've got up here in blue? Okay, so we've got some data in our table here. For example, if x is equal to 35, then f of x is 60, and g of x is 2,197. Okay, so we got x values and then outputs for 2 different functions, f and g. And it turns out that one of these functions, either the f row or the g row, one of them is an exponential function and the other one is a linear function, and our job is to figure out which one is which. So first observation is about the x's. What do you notice about the x's? That's plus 5, right? And the next one is plus 5 and plus 5 and plus 5 and plus 5, right? But it's important that they're the same because what we're about to say relies on them being consistent. Okay, let's take a look at the f numbers. What do we notice here for the gain? That's a plus 10, and the next one is plus 10 and plus 10 all the way through. What kind of a function increases by 10 every time we have the same change in x? It's a linear function. So that one is for sure a linear function. Yeah? Can you tell me what the slope is? Is it 10? Right, we were just changing by 10. 2? Why is it 2, Nala? Yeah, we're going up by 10, but we're going over 5, right? The 5's in the top row tell you you're going over 5. So up 10 over 5 10 over 5. That's your rise over run. So yeah, slope of that guy is 2. Okay, let's take a look at the last row. Up by how much here? 300. Over here? 390. That's too bad. Over here? 507, I think. I've seen enough. Linear or not? No. So there must be some other way to identify. I mean, I said 1 is linear, 1 is exponential. So clearly that's exponential. But we need a calculation that we can do to verify that it's exponential other than just process of elimination, because, you know, it's not the linear one. Just like we did this plus 10 plus 10 plus 10, and that was evidence. Oh yeah, it's a linear thing. So what we're going to do is not consider these guys here, but instead consider something else. What I'm going to ask you to do here is divide 1,300 over 1,000. We don't need a calculator there. What is that? That's 1.3. Okay, so we're dividing 1,300 over 1,000 is 1.3. And then over here, we're going to divide what by what? 1690 over 1,300. And that one probably we do want a calculator. What is that? That's 1.3. And then here, what divided by what? 2197 over 1690. And on the calculator, 1.3. And this is an exponential function. This is how you recognize that something is exponential. Because what this means is that every step to the right, we got to multiply the previous answer by 1.3. Yeah? If I have 1,000 and I want to turn it into 1,300, I can multiply 1,000 by 1.3. Or I could multiply 1,300 by 1.3. Or I can multiply 1690 by 1.3. Yeah? And if I just keep repeatedly multiplying by 1.3, well, isn't that 1.3 to some power? And isn't that an exponential thing? Just keep multiplying by the same. And so you guys are really comfortable this idea of, oh, to determine that it's linear, I just look at consecutive differences. Great. And as long as it's the same number like those plus 10s all the time, it's linear. So it's just a different way to explore whether or not something is exponential. It's not consecutive differences, it's consecutive quotients. So you just divide next number by the previous number, and as long as it's consistent, it's going to be exponential. Okay? Here? Yes. Here. Nod your heads. Yes. Yes. Okay. So coming down here, just kind of a summary of some stuff, and then you'll do the activity. This first formula, 1,000 plus 1,000t, it's one that we started with the rabbits. The growth of this linear function is additive, meaning we kept adding the same number over and over again, plus 1,000, plus 1,000, plus 1,000. But in this example, the 1,000 times 2 to the t, that was exponential. And if you just look in that row in your rabbit table, you kept multiplying by what? So you get one number to the next. In the second rabbit table, multiplied by what number to just go across the bottom row there for the rabbits? It started as 1,000, and then it was 2,000, 4,000, 8,000, 16,000. Times what every time? Times 2. 1,000, 2,000, 4,000, 8,000, 16,000. So the growth of an exponential function is multiplicative, meaning for each year that passes, we multiply the number of rabbits by the same thing. In this case, it's 2. Okay, so a couple of formulas that will hopefully kind of look familiar. I know we usually do like y equals mx plus b. I'm going to do y equals b plus mx just so it looks like what's here. So the output, that's my y, is the initial quantity, that's the b, right? You start on the y-intercept. And then the rate of growth, what is that? That's slope, right? And then multiplied by the input, which is x, number of years, something like that. Okay, and then for the exponential stuff, y equals, so I'm going to use, what letters did we use the other day? I think we used this, a times b to the t. I think that's what we used the other day. Okay, so y, that's the output. Initial quantity is which letter? It's a. What was it for the rabbit 1,000 times 2 to the t. What's the initial? Is 1,000. It's the a. It's the number sitting there beside the 2 to the t part. Okay, the growth or decay factor is what letter? B. What was it for the second rabbit equation? 2. Just a factor, meaning you multiply over and over again by 2. Okay, and then raised to the input, that's our t, number of years. Okay, so I think that's good. All right, so the activity starts on the next page. If you finish all of that before we run out of time, you can start on that homework, which is the page after the one you're on, okay? Raise the flag if I can help.